Hi girls, next we are going to see about a rolling motion, and rolling motion is a very common phenomena in our daily life. Suppose you consider the rolling of a disc on a horizontal surface, that is if you take a plate, any plate, and suppose if you roll it, and what are the several phenomena, that is several translation motion, rotational motion that take place in the disk. We shall see that now. And when you see this diagram, this is the disk which is rolling on the horizontal surface, and the center dark point is called the center of mass. In this, the center point is called center of mass. When the disk rotates along the horizontal surface, the center of mass will move only in the translation direction, that is in the straight line direction. Whereas when you see any point on the edge of the disk, it will move in the cycloid path, and this blue line represent the cycloid path of the edge of the point at the edge. Suppose if we take this is the point at the edge, and if the disk rotates, this point will take the shape of the cycloid. So you see this line, the only difference is the center of mass takes a straight path, but all the other points undergo a path which has a combination of the translational and rotational motion. That means the point which is at the edge will take both translational and rotational motion. So the point on the edge will undergo a path of the cycloid. Now when you see this, the center of mass has only one velocity, that is Vcm. Vcm means velocity of center of mass, that is equal to V trans, that means translational velocity. Whereas all the other points at the edges will have two velocities, one is V trans and other is V rotation. And you know V rotation is equal to R omega. So here we are going to take the center of mass, that is center point, the velocity Vcm, and the rotational velocity is V rotation, and single V is the resultant velocity. So here Vcm means velocity of center of mass, that is translational velocity. Whereas when you here it is with respect to center of mass, here with respect to point of contact. That means from the point of contact, when you see again the same Vcm, V rotation, and the resultant is V, and Vcm is always equal to V trans, because the center of mass will always move in a straight line. And so with respect to point of contact, when you see the dotted line will show you that this motion is considered from the point of contact. So here in pure rolling, the point of the rolling object which comes in contact the surface is at momentary rest. So when you see this rolling object, and when you see at the point of contact, it will come to momentary rest, for that is for a particular time it will be at rest with the contact surface. And so here when you take the pure rolling, you can consider that in two different ways, that is a combination of translational motion and rotational motion about the center of mass. So taking the center of mass, you are taking both the translational motion and rotational motion, and otherwise you can consider the momentary rotational motion about the point of contact, because at the point of contact there will be momentary rotational motion. So when you see here in this diagram, this is motion of the Cm, that is center of mass will always move in the translational direction. So all the points here, the black dots, will be from left to right. Whereas here the object we are considering the rotational motion, then the velocity is different. Vcm at the topmost point is from left to right, whereas at the bottom, since the object is rolling, it is from right to left, and the other points upwards and downwards. So this is a rotational motion. When you see the combination of this, you have to find out the resultant velocity. The resultant velocity, when you take the topmost point, at the topmost point the two velocities are added up. So you will get a 2 Vcm, and the center of mass the velocity is V, and when you see at the point of contact the velocity is 0, because in this diagram Vm and minus Vm. So both of them will act in the opposite direction. So at the point of contact the velocity is 0. So here we are considering the translational motion plus rotational motion, which will give the motion of at the point of contact with reference to the point of contact. And so here in pure rolling, so when the object will roll, you are having only v trans and v rotation, whereas v trans is always equal to vcm, that is velocity of center of mass. And so vcm is usually given r omega. R is radius of the rotating disk and omega is angular velocity. So when you consider two motions, one is rotational motion, the other is rolling motion. Rotational motion means the object just rotates. So that is when you see the clock, the needles in the clock will rotate. So that is rotational motion. There is no translation motion in the clock. Whereas when you see the rolling motion, you can take the example of the wheel. So the wheel is having both translational and rotational motion, whereas the needles in the clock will have only rotational motion. So they move only in the rotational path. So here in the rotational motion, we have the relation v is equal to r omega, whereas in rolling motion, you are having both rotational motion and translational motion. So here when you see at the topmost point, the v trans and v rotation are equal in magnitude and the same direction. So they are added up. So here when you see at the topmost point, they are in the same direction. So you have to add. So the velocity at the topmost point is 2 vcm, where vcm refers velocity of center of mass. So when you see this diagram, first diagram is pure translational motion and the second diagram is pure rotational motion, and they combinedly will give the velocity like this. So at the topmost point, the two velocities are added up, and at the bottommost point they will cancel, whereas at the side, that is from the left side and right side, they are having the resultant velocity, and vcm is always in the from left to right. And next we are going to see about a very important topic, slipping and sliding. So the body will roll only if the coefficient of friction is greater than 0, that is mu is greater than 0. The object will speeds up or slows down depending upon the velocity or acceleration we are giving. In this slipping and sliding, first what is sliding? So when sudden brake is applied, you take that example, then you can understand very easily. When sudden brake is applied, v translation is greater than v rotation. That is when you drive a car and give sudden brake, then the translational motion will be greater than rotational motion because the wheel is going to rest. So vcm is greater than r omega now. Here when you see this diagram, this is the example for sliding. That is, imagine you are applying a sudden brake to the car. So what happens here? V trans is greater than V rotation. Here the orange line represent V trans and the green line will represent V rotation. So here definitely the car is going to the car is coming to rest, and so V trans is greater than V rotation. So the V frictional force, that is Fk, will act in the opposite direction to V trans. And so what is the resultant velocity? This V, that is yellow line, will give you the resultant velocity. So that is along V translation, because V translation is very high. This is a case of sliding, that is you are applying a sudden brake to the car and V trans is higher than V rotation. So the resultant velocity is along V trans and the frictional force will always act in the opposite direction to V trans. This is a case of sliding. And when you see the next topic, slipping, for that you better consider an example. The vehicle is stuck in mud. Suppose the vehicle is stuck in mud, what happens here? The V rotation is greater than V trans because the car cannot again move because it is stuck into mud. So definitely the wheel will be rotating continuously, but there is no translation motion if the car is stuck in mud. So you can take V rotation is greater than V trans. In that case, the kinetic frictional force will always opposes the relative motion. So here, when you see here in this diagram, this is example for slipping, and here definitely V rotation is more. So the resultant velocity V is along the direction of V rotation, because always the resultant velocity will be in the direction of greater vector, and the frictional force is now opposite to this relative velocity V. So Fk represents the frictional force. And so when you consider the sliding and slipping, you have to consider these two examples. For sliding, you can take the sudden brake example, and for slipping, you can take the example of the vehicle stuck in mud. So in both the cases, in the first case, rotation, that is V trans is greater than V rotation, whereas in the second case, V rotation is greater than V trans, and you have to write the equations according to that. And next we are going to see about kinetic energy in pure rolling. So you take the wheel that is rolling on a road, and you have to find out the kinetic energy. So here the kinetic energy is the combination of two, that is kinetic energy due to translation motion plus kinetic energy due to rotation motion. Because the wheel is moving in the straight line path, that is translation motion, also it is rotating. So it is a combination of two kinetic energies. In such a case, translation kinetic energy half mv square, that expression you have to take, and instead of v can write v cm square. Cm represents center of mass, and for ke rotation you can write half icm omega square. I means moment of inertia and omega is angular velocity. And so here you can substitute, you can have two cases now with the center of mass as reference. So this is the wheel and the center point is called center of mass. And suppose if you take the center of mass as reference, you can substitute now I is equal to mk square, and you can substitute where k is radius of gyration, and you know vcm is equal to r omega. Substituting that, you will get this, and you can take half mv square outside. Inside the bracket you will get 1 plus k square by r square, where k is called radius of gyration and r is radius of the wheel. So this is the case when you take the center of mass as reference. Now you can take the point of contact as reference. So in such a case, you can have only the momentary rotation. You don't have the combination of translation and rotation motion. You have only the momentary rotation. In such a case, you can take only one expression, that is kinetic energy is equal to half I naught omega square. And you know parallel axis theorem. According to parallel axis theorem, I naught is equal to ICM plus MR square, and so ICM can be substituted as MK square, and so omega is equal to VCM by R, that is from the expression V is equal to R omega. So substituting these values, you will get kinetic energy is equal to half mk square plus mr square and V square Cm by R square. Now we can expand this. Multiply half mk square cm square by r square plus m vcm square by 2. You can take half vcm square outside. Within the bracket 1 plus k square by r square. So when you compare the equation 559 and 560, both are same. So either you can take the center of mass as reference, or you can take the point of contact as reference. So the center of mass means the center of the wheel. So here this red dot will show the center of mass, and here this diagram, this red dot is the point of contact of the wheel with the surface. So in both the cases you are getting the same expression, which means that whether you can take in both the cases are suitable for the kinetic energy in pure rolling. Next we are going to see about rolling on inclined plane. So when you see this diagram, this is an inclined plane which makes an angle theta with a horizontal surface. An object is rolling on that. So when the object is rolling, there are two forces acting, mg acting vertically downwards and the normal force which is perpendicular to the surface. And this mg is resolved into two components, mg sin theta and mg cos theta. And theta, if this angle is theta, in the diagram the other angle according to angles law, that angle is also equal to theta. So here mg cos theta is balanced by normal reaction, so both of them will cancel. Whereas when you see mg sin theta and f, they are opposite in direction, whereas mg sin theta is from left to right and frictional force is from right to left. So for translational motion, you have to consider mg sin theta minus F is equal to ma. Here F means frictional force. Here this is given negative sign because it acts in the opposite direction. So this is equal to ma. This is for translation motion. And for rotational motion, since the object is rotating, you can take RF. RF represents tau because tau is the moment of force. So force into distance will give you RF. RF is equal to I alpha, where I is moment of inertia and alpha is angular acceleration. And you can say that A is equal to R alpha because you have A acceleration and alpha angular acceleration. So A is equal to R alpha, which means that alpha is equal to A by R. So what about RF now? You can substitute for I and alpha. So mk square into A by R, or you can bring the R to the other side. So F is equal to ma into k square by R square. So from this you can substitute this F, that is mg sin theta minus F is equal to ma. In this you can substitute F, and so the equation now becomes mg sin theta minus ma within brackets k square by R square is equal to ma. Throughout this you cancel m. So A of 1 plus k square by R square is equal to g sin theta, or A is equal to g sin theta by 1 plus k square by R square. So this is the equation of acceleration for rolling on inclined plane. Here k is radius of gyration and R is the radius of the circular object, and theta you know the angle, and g acceleration due to gravity. So next we are going to find out the expression for velocity of the rolling object by using third equation. And you know the third equation is v square is equal to u square plus 2as, and here the initial velocity becomes 0. So v square is equal to 2as. And you know from this diagram what is sin theta? Sin theta is opposite by hypotenuse. So h by, suppose if the length of the inclined plane is s, you can write sin theta is equal to h by s. So in this equation v square is equal to 2as, you can substitute 2, and acceleration you have derived one expression, substitute that, and instead of s you write h by sin theta, and sin theta get cancelled. So you will get 2gh by 1 plus k square by R square. This is the expression for v square. So you can take square root, that will give you the expression for velocity of the rolling object. And next we are going to find out time taken for rolling down the inclined plane. For that v is equal to u plus at, and in that since the initial velocity is 0, you can substitute u is equal to 0. So you will get a t is equal to v by a, and you know what is v and you know what is a. So substituting that, you substitute v, square root of that expression, and you substitute a. In that g and g get cancelled, square root of g and g get cancelled. So you will get a 2h, and so within square root you bring all the terms to this square root side. So you will get 1 plus k square by R square the whole square, g square sin square theta, and so g and g, 1g will get cancelled. So you will get 2 square root of 2h into 1 plus k square by R square by g sin square theta. That is, you bring this term to this square root, then that will become square. The whole term will become the square, and so cancelling that you will get the time period for rolling down on the inclined plane. So we are getting for both acceleration and velocity the expression. And here when you see this, the radius of gyration is in the numerator, which shows the least value of radius of gyration will take that is less time to reach the bottom. So we will reach the bottom of the incline first. So the least value of radius of gyration k will reach the bottom of the incline first. So when you take this disc, ring, and every object which will have least gyration will reach the bottom first. That's all, girls. Hope you understand.